Tá bom.
Okay, so it's a pleasure to have Guilherme Brando to give this special seminar today here at IFT and SAIFR. So Guilherme, he did his PhD at Federal University of Espírito Santo, and actually his PhD thesis got a prize, honorable mention in this, what is it, Gravitation Thesis Prize. ICTP-SAIFR PhD Gravity Prize. This was 2023.
Yeah.
So during his PhD, he spent some time visiting Portsmouth. And then after his PhD, he got a postdoc at the Max Planck Institute for Gravitational Physics at Potsdam. And now he's transitioning to another postdoc in Durham. But he also recently was hired at the CBPF, Centro Brasileiro de Pesquisas Físicas, which is a very good thing to have Guilherme back in Brazil. So he's coming back eventually.
Yes,
he's coming back.
Next year.
Next year he'll be here in Brazil, and hopefully we can establish some collaborations. So Guilherme is an expert in several aspects in cosmology, and I think most recently he's doing some work using exploring the nonlinear scales in cosmology, which is a very important and difficult subject. So today he's going to talk about emulators for beyond-LCDM models and photometric probes. So thank you, Guilherme.
Yeah, thanks, Rogério. Thanks also for the invite and for having me here. Yes, so just another disclaimer once again. This is the pointer, isn't it? Yeah. It's UNESP, not USP. So it was also 21, not 20. Yeah, and today I'm going to talk about this recent works that I've been doing, also in collaboration with João, who is here, and Vivian, who is also in online remotely. So since I just left the AI, I still use everything that was the same template. And yeah, so let's start. I'll try to do a little bit less technical because normally the more technical, the less interesting is the presentations. So I'll start with just outlining some things about the universe so far. So for instance, we have the standard model of cosmology. It's called lambda-CDM. Lambda for dark energy, the cosmological constant, and CDM for cold dark matter. Dark energy, which is my major interest in cosmology, is it's the 70% of the universe, more or less, and then we have dark matter with 27%, and the rest is ordinary matter. Ordinary matter is everything that interacts with different things besides only gravitationally wise, because dark matter so far has only interacts via gravitational interactions. Okay, and dark energy is the main driven. So, for instance, it's the explanation that we have for the current acceleration of the expansion of our universe. Just a brief slide that I always have to put here because I'm always talking about beyond-LCDM theories. So this is just a slide where I put everything that people like to put in the introductions of papers of beyond-LCDM. We have the cosmological constant problem, orders of magnitude of discrepancy between the theoretical prediction of the vacuum energy and the observational one. They are like 60 orders of magnitude apart from each other. This is an old problem. This is an interesting problem, but it's more used as a motivation in the past. Nowadays, we have cosmological tensions. We have the Hubble constant tension, which is outlined here in this plot. We can see that the CMB values are like the values that we infer from the CMB is lower than the ones that we can actually measure using Cepheids and the tip of the red giant branch as calibrators. We have something that I really like, which is stress tests of the concordance model. So the standard model of cosmology can be seen as a concordance model. So it's either a fundamental theory or something that we can have a limit that we need to fall in it. Okay, and something that I have worked during my PhD, which is cosmological tests of gravity. I also put this plot over here for the W0WA recent constraints coming from DESI. Okay, so the first data release. So we can see that when we combine DESI, BAO, CMB, and supernovae, we reach almost like 4 sigma in discrepancy. So this is a very interesting result, but it's a very new result. It's something that we are now going to higher redshifts with DESI. And basically, we still need to take some care with this. It's not attention per se, because there has been recent work in the literature that rephrases this type of, for instance, analysis in the sense that supernovae actually prefers a very different total matter energy density than what we have from BAO and CMB. So even though this is very interesting and is going to motivate us to look for different theories, we still need to understand a little bit better what's happening here. And that's what is so exciting for the upcoming years. So besides that, the standard model of cosmology, we have something that is the cosmological principle. We require, or we impose, for instance, that at large scales, the universe is homogeneous and isotropic. We can see this from this Planck map. These are the fluctuations in the temperature in the sky, okay? We can see that the fluctuations are basically of the order of 10 to the minus 5 Kelvin. So this is a very strong support to the cosmological principle, okay? And basically, the formalism that we have to describe the universe in large scales is when we impose homogeneity and isotropy in the Einstein field equations, we are left with the Friedmann-Lemaitre-Robertson-Walker metric, which is given by this line element here, okay? And when we also impose the same thing for the right side of the Einstein field equations, the matter content in the universe is constrained to be given such as of a perfect fluid, where the 0,0 component is the energy density of the species in question, and the other ones are the isotropic pressure of the species. Okay, so perfect fluids, they can be connected via the equation of state parameter, which is just the ratio between the pressure and the energy density, okay? And just to understand a little bit better what we have, the different things that we have in the universe, I'm showing here like some of the ingredients that we have. So CDM and baryons, they have basically they have the equation of state is they're pressureless, okay? Baryons in the early, they're coupled, so it's not 0, but we don't care about that. In the background, they're always 0. Photons and massless neutrinos, they have that the equation of state is going to be 1/3. Dark energy as a description of a cosmological constant is -1. And what is interesting is that massive neutrinos, they transition from the early time where they're relativistic. So 10 to the 4, for instance, we can see that they're 1/3. And then they're going to transition at late times to be just another component of dark matter, okay? So I'm showing here in this plot the evolution of different masses and different types of massive neutrinos. So this is something that we can do already, which is fairly easy to test the mass of the neutrinos, okay? And just to finish this part of the background, when we put everything back in the Einstein field equations of motion, Einstein field equations, we're left with the Friedmann equation, with the Friedmann equations. First one is just a constraint. Okay, it's going to relate more or less how much all of the density of the ingredients that we have in the universe, and also we have the curvature. And the second field equation is just the Ray-Chalduri equation, which is the equation that is going to give the evolution of the scale factor. The scale factor is connected to the redshift, and so we have that this is just going to control how much the universe expands. Okay? We observe different things in the universe. So when we look up, we just don't see a homogeneous and isotropic thing in the sky. We observe structure, we observe galaxies, clusters, stuff like that. And the basic principle that we start to describe these things is that at first order, we can simply perturb the metric tensor and also the energy content. And this gives us the perturbed Friedmann-Lemaitre-Robertson-Walker metric. Here, I already specified a gauge because it's easier for us to understand. The psi potential is going to be just the one that is going to be connected with the Poisson equation, okay? Phi is just a curvature perturbation. And this is also a specific form of the energy momentum tensor. if I had written this engaging variant terms, that will be in the T0J component. There will also be the perturbation of the lapse. But I'm not going to discuss this kind of things. So I just want you guys to understand a little bit or have familiarity with the metric tensor, with the metric element given in these terms, and also the energy content described by perturbations in the energy density, perturbation in the velocity of each species, an isotropic perturbation in the pressure, and an isotropic perturbation of the matter content as well. Okay? So the success of both of these descriptions, so the background and the first order perturbation theory, led us to the success of the Planck mission. As we can see here, we can easily compute and have developed a lot of numerical codes that are very fast and accurate. They're flexible, they're called Einstein-Boltzmann solvers, and they are very easy to evolve the universe from a very early time in the universe during radiation domination, which we can see here in the left-hand side. We have that in the beginning we have more domination of photons, ultra-relativistic species, which are massless neutrinos, and then also just massive neutrinos, which is given by the red curve here. And on the right, I'm just showing the angular power spectrum of the temperature fluctuations of the Planck mission. You can see that we have very small error bars when we go to small scales. So these codes, they have given us and like pushed us to a very, to this new era where we call precision cosmology, not only from the data side, but also from the theory side, okay? And to describe and to understand what I'm going to talk about today, it's always good to understand what is the matter power spectrum, which is at linear order also computed by these numerical codes that I just mentioned. Before understanding the linear matter power spectrum, it's good to understand what is the two-point correlation function. So the two-point correlation function is going to measure the excess or the probability of finding for instance, the probability of finding two things next to each other. So basically here on the right-hand side, we can see that it's going to measure the difference, so the density perturbations between 2 points, okay? So these are just galaxies, but I'm just mentioning I'm going to talk about the matter power spectrum today. So the ensemble average of the density perturbation, so the two-point correlation function here, is just going to be the psi, which is just the two-point correlation function in real space. It's just because we just need and are interested in the modulus of the difference between the 2 points because we have isotropy, okay? And what is the linear matter power spectrum? It's just the Fourier transform of this. So on the right-hand side, I'm just showing the linear matter power spectrum for different masses of neutrinos. I think that they are all of the same type, so 3 degenerate massive neutrinos, okay, with normal hierarchy. And on the left-hand side, we can see that it's very easy to compute what is the correlation function from this linear matter power spectrum that is given by these codes, okay? Also in the correlation function, we can see that the second peak here is going to give us the BAO, is more or less the distance that is imprinted in the galaxies from the universe in its early periods, okay? And in Fourier space, this bump here is just going to be translated to these very rapid oscillations in the linear matter power spectrum. And since I don't know if everyone is familiar with what is the nonlinear version of the linear matter power spectrum, I'm just showing here the same thing that I showed before, but now I'm overplotting not only the linear matter power spectrum, but also the nonlinear one. And we can see that when we allow gravity to become nonlinear, so for instance, we allow the density perturbations to exceed a very small value, we have gravitational collapse, and then the nonlinear matter power spectrum gets bumped at small scales, but at large scales is going to be the same thing as the linear matter power spectrum.
So the nonlinear power spectrum is from simulations or something?
So both of these, here I just wanted to show like a very rough thing. So the linear one is just from an Einstein-Boltzmann solver, and the nonlinear one is just the halo fit prescription. So it's it's an old fitting formulae, but it's calibrated with numerical simulations. And this is not a very, for instance, very well measured or like a evaluated quantity, this nonlinear matter power spectrum. It's just, I just wanted to give an idea of what is going to happen in small scales when we compare to the linear one.
Are there data that would fall on the nonlinear and not on the linear, or vice versa? Are there?
Data points
Yeah,
on
I
the...
mean, is it necessary to explain some data there?
Yeah, so we need to go nonlinear to explain data, like data that we extract from surveys. So with spectroscopy, we're not going to go that deep. We're going to be like more or less like here, which is quasi-nonlinear, very mildly nonlinear. But with, for instance, cosmic shear that I'm going to be talking about today, which is photometric probes, we need to go to very nonlinear scales. So, for instance, this nonlinear matter power spectrum, like a very good modeling of the nonlinear matter power spectrum is needed. Okay? Does this answer your question?
No, maybe you'll go more in detail later.
Okay.
And I will ask later again.
So yeah, so now I'm going to be talking a little bit more in detail. So far we have had only stage 3 surveys for photometric probes, so photometry surveys. We had the dark energy survey, we have the HSC, and also KIDS, Viking, I don't know. A lot of them. I don't know if Vikings is photometric. But the collaborations so far have used this old fitting formula that I just mentioned. So for instance, the halo fit prescription to model the nonlinear matter power spectrum. And why is that? It's basically because the precision requirements for the modeling of this spectra, they were not as stringent as we needed. So basically, what I'm showing here in this plot is just the difference, so the ratio between a nonlinear matter power spectrum between two prescriptions, the HM code and the Euclid emulator 2. So we can see that they have very big discrepancies at intermediate scales, where we are in the BAO scale. And also, we have very weird shape dependencies in small scales. So this is basically, this is telling us that they are not in agreement. They're very bad. However, when we go to, for instance, to the level of inferring cosmological constraints, we can see that even if we get different, for instance, very different nonlinear matter power spectrum, the dark energy survey, for instance, the SU3, this paper that describes the modeling strategy and the validation, we can see that each of these points in the middle here, which are basically different codes to evaluate the nonlinear matter power spectrum. So baseline is the halo fit, cosmic MU, and Euclid MU are different emulators, and HM code is just one of these fitting formula. So even though they are not in agreement here, but they are more or less, they cannot be distinguished between each other. They're not biased in the results because they are all in agreement in below 0.3 sigma deviation between each other. So for the stage 3 surveys, we really didn't have the precision. We lacked precisions to differentiate between the two, between all of the 4 or more. And these quantities here, they didn't bias enough the results, so we needed more modeling. But in stage 4 galaxy surveys, we need that. Here I'm just showing 3 of them. DESI, the dark energy spectroscopy instrument, which is already online. The Euclid satellite, it was launched last year and is going to have its first data release next year. And the last one, the Vera Rubin Observatory, which was called previously LSST, or I think it's also still called LSST, but the official name is Vera Rubin Observatory. And due to the increase in constraining power for these surveys, we need to have a better modeling, not only for the lambda CDM side, okay, but especially for the beyond lambda CDM side. So we need to have very accurate predictions of this spectrum to actually get constraints that are credible enough from these theories. Just an example, we have for instance, one very simple parameterization of an evolving dark energy theory, which is the CPL parameterization. It's just a Taylor expansion, okay, where we have W naught that is going to be allowed to vary, and also WA, which is going to be related to the first-time derivative of the dark energy equation of state. And we can see that, so for instance, if we focus here on the left-hand side, the difference between the red contours, which are stage 3 surveys, and the blue contour here, which is going to be the 3x2 point correlation function analysis in the end of the LSST timeline, we can see that there has a very big difference between the two of them. So basically, we are going to be way more sensible in W0 and in WA when we go to stage 4 surveys. And this can also already be seen when we go and see and inspect again the same contours that I showed before from the DESI paper. They are already for instance, in 0.2 difference, more or less, when we take in W0. And we can see here that it's basically what we were getting and hoping to get in this forecast into 2018 for the LSST. They're not the same thing. Obviously, they're not the same strategy or like survey, but this gives an idea that we're going to get even better constraints already in a very simple parameterization as the CPL one. So I don't know if so this was a talk that I was preparing for a more general public, an audience. So I thought about just talking a little bit about what is weak lensing cosmology. So the physical setup is basically this. So we observe, so for instance, x is going to be the distance or the size of the source object, okay, the unlensed source object. And we're basically interested in understanding how this separation vector, dx here, which is going to be related to this deflection angle, involves in this clumpy universe that we have and see in the skies, okay? So basically, the surface density of the source is unchanged, and this is basically going to relate the angles or the sizes of the objects unlensed by this distortion matrix Aij here. It's worth understanding that weak lensing cosmology is just a purely statistical effect. We don't resolve a single event, and because basically it's just too small to be detected. But since we have a lot of galaxies in the sky, we go from 10 to the 6, 10 to the 7. I don't remember now in DES year 3. I think 10 to the 7. To basically 1 billion now with LSST and Euclid survey. So if we add up all of these small deviations, we get enough signal-to-noise ratio so we can constrain the evolution of the universe and also the growth structure of the universe, okay? I think this, yeah. So now it's okay, interesting, this picture. Yesterday it was not good. So the distortion matrix is going to be characterized just by the convergence and shear, okay? It's a symmetric matrix. And from the lens equation, which is a geometrical relation that we get from the previous setup, okay? That is going to relate all of the angles that we have here. So what we end up having in weak lensing cosmology is just that the source is going to, which starts as a circle, can be increased. So if we only have convergence, so it's going to be bigger. And if we have shear, it's also going to become more elliptic. So since it's a small, very small effect, so the lens equation here, we can just linearize it. And then this is what we call as the distortion matrix, which is going to capture and relate what we are interested to compute. I think this is I made a mistake before. So just jumping ahead a little bit and not explaining in detail. So this Aij matrix here, the distortion matrix is going to be related to the Poisson potential phi. And the Poisson potential phi is just going to be related to the matter density perturbations via the Poisson equation. So in the end, we're left with this kappa theta here expression, where we have the density perturbations. Now I go here. And if we compute the same thing as before, the two-point correlation function in the sky now, so the convergence at 2 different points, and impose isotropy and homogeneity, we are left with the power spectrum of the convergence field, and we are usually working with the angular dimensionless power spectrum, which is this Cij kappa kappa, and L is the multiple, okay? Here is the nonlinear matter power spectrum that we are interested in increasing the precision in our modeling, okay? So also, since I didn't know that people would be familiar with weak lensing cosmology, basically the other function here, it's called the lensing efficiency. And it's just going to be an integral because we have to weight different tomographic, different bins, source bins. So these are the source bins of the survey. For instance, we have different, we're going to detect and target different galaxies in a very wide bin because we don't have precision in our, we don't have the redshift in photometric surveys. And when we compute this integral here, we are left with a very smooth and pretty function. Okay?
I was wondering, like, for example, when you are trying to compute correlation functions for galaxies, you usually have to take an extra step when trying to go to nonlinear scales, trying to, for example, modeling the nonlinear galaxy bias or something like this.
Mm-hmm.
I was wondering, like, for the convergence field or in weak lengthening analysis, do you also need to go to some modeling beyond the usual only power spectrum, or do you have to also the convergence field behave differently under linear scales or something like that?
So this is a very good question. So in this talk, I'm just going to talk, even though I say photometric probes, I'm just going to talk about cosmic shear and the convergence field and also the shear field. They're directly related to how the matter density distribution in the sky. So we don't have, so galaxies are tracers of this underlying density field. So to describe it, we start from this linear order, just bias prescription. And when we add nonlinearities, we need to go beyond this linear order. So for matter, we are already sensible to directly the matter density field. So dark matter is already there. So we don't need to do an expansion of a bias tracer. Okay. So
Can I complement this answer?
Yeah.
You do have intrinsic alignment. So there is the possibility that in very, very small scales, you have to modify your intrinsic alignment modeling. We are not at that level yet.
Yeah, exactly. So since I'm not going to talk about intrinsic alignment because in this project we didn't do anything about that, I was going to omit. But yeah, thanks, Vivian.
So just to continue a little bit, so you will be using the nonlinear part of the power spectrum, but then you will not consider nonlinear effects in intrinsic alignment or other effects.
No, we do consider nonlinear effects. We consider the NLA parameterization, which is supposed to encompass nonlinear effect. Is it the best model in the literature? Unclear.
Okay.
I know, there are other possibilities.
Okay, great. Thank you. Thank you.
Yeah, thanks for the question, and thanks, Vivian, to compliment. It was good. Yeah, just to summarize in the end, this is what we get. So we observe the shear image of this very pretty galaxy here, and it's very distorted. In terms of what we have in an embodied simulation here, we have like a snapshot, we have the CDM distribution, and the galaxies are going to be following more or less this distribution, and all of the galaxies are going to be these points that are going to be elliptic here. So I don't know how I'm doing with time, so I'm going to pick it up a little bit. So the part that I wanted to talk about is nonlinear scales, why we want, so more or less when nonlinearities they start to be relevant. It's more or less, well, I like to see in this way. I love this plot because I made some time ago for a project. And it basically just is just a color bar in terms of the ratio between the nonlinear metaphor spectrum and the linear. I truncated here this ratio to 4%, but it actually exceeds this value. Okay, it goes to more or less like 35. But if I just use from 1 to 35, it was not clear enough to see the deviations in terms of the colors. Okay, but it basically says that this is the Euclid footprint. So these red lines here is what Euclid satellite hopes to deliver in terms of cosmic shear. So basically, the scale cuts in the Euclid survey, they're performed in harmonic space already. This is the optimistic prescription that they use. The minimum multiple is going to be 10, and the maximum one is going to be 5,000. Okay, and we can see that in at really low redshift, we can go to really small scales, almost 7 K inverse megaparsec. But when we go to higher redshifts, the scales, they were going to be following these blue lines here, which are just going to be the relation between the multiple and the comoving distance, okay? But so since we are going to be, so we need to think this in terms of, for instance, even if we're not going to be observing rectangle, so basically we don't expect to detect or like to model nonlinearities going to k equals 7 in a higher redshift, precisely because the universe is expanding, okay? These other curves here I just show for comparison, they are just the cosmological horizon, okay? So in z equals 0, they're almost like 1 gigaparsec, the size of the cosmological horizon. And then these other ones are just like multiples of this cosmological horizon that I use. So with perturbation theory, we simply cannot go to very small scales because we're always limited to the assumption of small density perturbations. And this gets us to the mildly nonlinear regime. But cosmic shear is something that probes really small scales. So basically, this is not going to be enough for stage 4 requirements. And the most predictable alternative that we have in the literature to explore these small scales is precisely using n-body simulations. So, yeah.
If you go back to the plot,
Yeah.
just a curiosity, I would expect that when you go to high redshifts, linear perturbation would be better than at small redshifts. So I would expect this plot to go, light green like that. But you see, there's a small. I can see there's a small effect. But so my intuition would be, okay. So this is 3.5 is not a large enough redshift.
Yeah.
In order for linear perturbation theory to be much better, no?
Exactly. So we still have some nonlinearity that we need to model accurately there. So this is precisely the same question that Raul had yesterday, because he was expecting that at the higher redshift everything would be just linear. But we always have some nonlinearities, and precisely since the universe is expanding, we don't have just a straight line here. We have something that is going to be more tilted in that way.
Yeah. No. So, but Lyman alpha is usually what, 4?
So, Lyman alpha, yeah, it's from 2 to 5, I think.
2 to 5.
Yes. Okay. So, but there is a caveat here because Lyman alpha, you pass through a lot of stuff from us to them.
Yes.
So
yes,
so that you have like a lot of support from structure. In lower redshifts. But yeah, I can think about this in terms of, Lyman alpha or anything.
Actually, there is another feature of this plot that surprises me. I mean, the ratio is very small. I mean, 1.04. I mean, it's almost nothing.
No, this is something that I mentioned. So I truncated this. This goes to 35, actually. So to make this plot pretty, when I plotted from 1 until 35, there was almost no black. So dark green.
35 in redshift.
No, so the ratio here, it goes from, I have a plot that I'm going to show later that precisely plots this for different redshifts and different K. But this boost function here is way bigger than 4%. It's just for plotting schemes. I need to think about how to do this better. But it's basically because the dark green was only here, because it was linear scales. So even if I was plotting in log linear, it was not nice. But you're definitely right. This plot is going to be changed, but I liked it. But I'm going to show a better plot in a minute. So just to shock people, I like to put these equations that are like n-body simulations and linear theory. They're essentially the same thing because this is here. It's just the evolution of cold dark matter, and this is precisely what we get from the moments of the Einstein-Boltzmann of the Boltzmann equation of motion for a pressureless fluid. Okay, we don't have any collision terms. F here is just the distribution of the CDM field. Okay, and these equations here. This is the 0th moment equation, which is the continuity equation. This is the first moment, which is the Euler equation, and this is the Poisson equation. This forms the Vlasov-Poisson system that is going to describe the growth of structure, the growth of cold dark matter in our universe. But in an n-body simulation, we don't have a fluid description, we have particles. So the version that we're interested in solving this is actually a discretized version of this phase space distribution F here, where we hope, and this is something that we never talk about, we hope that in the limit that we increase the number of particles in our simulation, we end up with the continuity equation in a continuous version, which is precisely this one, okay? So basically, we are interested in solving for the force of particles in these simulations, and then moving them according to these two equations here, x and p, okay? And n bar here, it's just the average number of the particles in your simulation, okay? And the mass here, dm, is the particle mass, okay?
Would be easy to introduce fifth force, which is not related to gravity, in this type of formalism and in the simulations?
in the sense of like a modified gravity, or?
Yeah, so in the second equation there will be another contribution in addition to gratify.
So yeah, so basically when we have modified gravity simulations, is precisely what Rogério said. We will have this plus something that is going to is going to be the nabla 2 of the scalar field perturbations. Okay. So in this sense, we have this equation plus an additional equation, which is going to be the Klein-Gordon equation. Okay, so an equation that is going to be solving the perturbations of the scalar field, and then you have to plug it back in the Poisson equation.
Right. So is there? I know that there are codes that does this n-body simulation, but are there codes that you can actually easily introduce this fifth force kind of behavior?
Yeah, so the first codes that did modified gravity simulations, they were actually solving everything like at the same time.
Yes.
Okay, so they were also solving for the Klein-Gordon field equation.
Okay.
But the problem is that the Klein-Gordon equation is not a linear equation; it's a non-linear one.
Yes.
So you cannot use the same integrator or solver that you use for gravity in that as well. So you need like a different scheme and different algorithm to solve it. Okay. So this adds a lot of time. Okay. Okay, time and memory. So yeah. So the most direct way, and in the beginning of the works here in the 70s in body simulations, was to compute directly the force between the particles. This is the most intuitive way that we can think about, just computing this. But the complexity of this grows with the number of particles. It grows with n to the square. It's not ideal for cosmological simulations that we require to have 10 to the 8 to 10 to the 11 particles in a box of at least cosmological size. So this is very unfeasible in terms of cosmology, because it's time-consuming, computationally expensive. And when we want to get constraints of parameters, cosmological parameters, we need to perform a full Bayesian analysis. We run a lot of Monte Carlo Markov chains that João is an expert on. And for instance, for a very traditional lambda CDM cosmic shear analysis, we sample almost 10 to the 5 points in parameter space. And it makes no sense to run 10 to the 5 simulations for each of these points, especially in beyond lambda CDM, because we might have the case as something that Rogério just said, where we have a beyond lambda CDM theory, which is modified gravity, and when we have an extra equation of motion to solve that is a nonlinear equation of motion, then this gets even more complex, okay? So we want to explore alternatives that are fast enough that we can actually test a broad spectrum of beyond lambda CDM theories. And in the 80s, people came up with this particle mesh algorithm, which is very interesting because it makes use of fast Fourier transforms, which the complexity grows of the number of grid points times the logarithm of this number of grid points. So we don't solve for the particles anymore, we solve for the potential. So we assign these particles that we have in our simulation to a mesh. We use some kind of mass assignment scheme, and we then solve for the potential in Fourier space by precisely using, for instance, Green's functions. And the Green function is going to depend on the mass assignment that we use to assign the particles to this grid. Here is just a schematic way of what we're actually doing to solve the Poisson equation. This is a very interesting idea because it's cheaper, but we don't solve for small scales, very small scales, because particles don't see each other. So basically, when we have put these particles in a grid, we're not going to solve anymore for the particles. We don't have the orbits of these particles, and we can also not solve the internal structure of halos. So basically, we really lose resolution if we want to do statistics or investigations in terms that we need to have a halo description of our universe. But, sorry. Oh. Oh, yeah. yeah, exactly. So there are many typos. I need to keep track of a lot of things. But yeah, this is an easier one because I didn't insult the institution that I'm in. But yeah. So particle mesh is just a trade-off between time and resolution. It's way faster, but then the bottleneck is the memory to solve this thing here using fast Fourier transforms. So just to give an example of what I actually use, it's an even faster approach, which is called the comoving Lagrangian approximation. It combines perturbation theory with the particle mesh algorithm. The perturbation theory, it's just because in large scales we know that the universe is well described by perturbation theory. And this allows us to speed up our simulations, okay? So it's effectively a particle mesh code, but in a different frame, okay? This is just the difference between two snapshots of a Cola simulation with 10 time steps and a gadget simulation with 2,000 time steps. This is very nice, but to the naked eye. But when we go to the spectrum, it's really not that good. Precisely because here it's a plot where I had some difficulties to explain yesterday, so I'm going to try to explain it better today. So here I'm plotting. First of all, I'm taking the reference as the BACO, higher resolution emulator. BACO has a very high resolution mass particle resolution. Because the particle mass is basically 10 to the 9. A low mass resolution simulation called PM, which is going to be these dashed green lines. PM, high resolution mass simulation, which also gets closer to the resolution of this BACO simulation. And the called AREPO. AREPO is just, in terms of gravity, it's the same thing as gadget, okay? They are just different in the subgrid physics, but in terms of gravity, they're the same thing. And what I'm plotting here is that we see that the agreement between a particle mesh simulation and a very fancy code like AREPO here is basically depending only in the mass resolution. And when we go to, for instance, k equals 2, it's a % deviation between the two. At the same time, when we use an increased mass resolution, the same particle mesh simulation here gets a below % agreement at k equals 2 with a higher resolution code. At z equals 1, exactly. So z equals 0, I expect this to be like between 1 and 2. And the problem is that direct comparisons in terms of matter-pore spectrum are not used anymore because basically we never emulate directly the nonlinear matter-pore spectrum anymore. And when we take ratios of ratios of ratios, not only the noise gets canceled, but we end up having some variance suppression at small scales, because not only we fail to resolve halo structure, but there is some very rough mode coupling thing here that starts around 0.6 that begins to alias your pore spectrum. So basically, we can cancel each other. We can cancel a lot of the issues and inconsistencies in a particle mesh code that more or less pushes too close to 3. But this is the best we can do in terms of beyond-LCDM, because beyond-LCDM can always add a lot of complexity. So it's unfeasible, or if we had all the time in a supercomputer in the world, I would just use AREPO or gadget. But we cannot. We don't have. We are on a time schedule, and we need to do the best we can with what we have. So particle mesh code, it's good for independent groups that don't have the very fancy resources that a national computer has. Just to finish this part of COLA, it's just to give an idea on the times on the wall clock. They have basically the same number of CPUs, so wall clock, and they were run in the same machine. So basically the wall clock here is precisely what we want to understand how fast COLA can be. The first line here is just a Gadget 2 simulation. And we can see that COLA gets 2 orders of magnitude down if we compare to this Gadgets 2 simulation. This is roughly the same simulation settings that one needs to use to go to k equals 3 in the matter-pore spectrum. In the end, I'm going to say that we don't know if going beyond k equals 3 is relevant to get cosmological information from, but save it for later. And what about the problem of cost of running n-body simulations? Like 10 to the 5 is still too much. And then that's where emulators come in to help us. They're basically just very strange nonlinear interpolation schemes that use machine learning algorithms to speed up. Okay, so we can reduce the number of simulations from 10 to the 5 to 10 to the 2, 3 orders of magnitude. And basically, they're just more trustworthy and a better way of sampling the parameter space that we have if we just use like something like a halo fit that would just perform fittings in terms of chi-square stuff and things like that. So basically, emulators are just smarter ways, black box methods to get something to run and to get a nonlinear prescription of the matter-pore spectrum in a fast way. Okay. So the thing is that in cosmology we have some very good state-of-the-art emulators, Euclid Emulator 2 and BACO. They have very high resolution mass resolution, so both of them have 10 to the 9 the particle mass is 10 to the 9 solar masses, so this is very good. And but this is only for lambda CDM cosmologies, because then there we can have the available time to run very fancy n-body simulations. But for beyond lambda CDM theories, we are never going to have the time in a federal computer to do this. Okay? Just some advertisement of what we have already in COLA. We have massive neutrinos with different masses. We can also use different hierarchies and do different things with it. COLA is well validated in terms of comparing it with Euclid Emulator 2 and BACO. At the same time, we have very, very different theories of modified gravity with different screening mechanisms. But all of these validations that we have performed so far, they relied on very exotic physics, but always with cosmological parameters that are very close to the ones from the best fit of Planck. And why is this a problem? Because we don't know what the universe data vector is. We need to be as agnostic as we need. We can end up going and probing regions of this parameter space that are very extreme in terms of values of these cosmological parameters. So they're very far away from the best fit ones. Like for sigma 8, we expect to be 0.8, something like that. And in the end, we may end up with something that is 0.6, which is very hard to perform n-body simulations, even if we have a very fancy code like Gadget or Arepo. So this gets even worse for particle mesh. So what we did, myself, João, Jonathan Gordon, a PhD from Vivian at Stony Brook, Bernardo Aguiar from CBPF, and Felipe Falciano from CBPF, we decided to validate COLA at the level of the observables. So we just chose one lambda CDM model, beyond lambda CDM model that is very mild, because we needed a reference to compare with. So we want to see how COLA is going to fare in the same way as I showed before from the DES Year 3 Krauss paper. If we could distinguish how much is going to be distinguished between different prescriptions. So COLA compared with Euclid Emulator 2. Our strategy is to create multiple fiducial data vectors spanning a very broad parameter space and stress test the performance of COLA. The parameter space that we used was the Euclid Emulator 2 one, and the surveyed specification that we chose was the LSS Tier 1 design, okay? So there's going to be a new Euclid Emulator 2, is going to be Euclid Emulator 3. They're going to use the same resolution, maybe the same number of simulations, but a little bit more, but with a broader prior in the parameters, okay? This is going to help us in weak lensing. So Ricardo, this is the boost. It took me it took a lot of time to get here, but basically at large scales it goes to 1, okay? And then when we go to small scales, it really gets amplified. So I'm going to think how I can improve that plot. So the quantity that we want to emulate is precisely this boost, because it's more well-behaved than the matter power spectrum. The matter power spectrum has features, shapes, not a lot of shapes, but still it's difficult for you to emulate something that is not as smooth as this boost function. And to reduce some noise issues that we have from when we use simulations, our strategy is to emulate the boost in that way that I show here, where we take a reference point from the boost of the Euclid Emulator 2, and then we're just going to extend this reference Euclid Emulator 2 point with COLA prescriptions. So basically, we're going to use COLA WCDM simulations to go beyond this Euclid Emulator 2 prescription that we have here as a reference. Just to talk a little bit about the emulation itself, we emulated the boost in that way. We used 3 different prescriptions to our emulators, Gaussian processes, neural networks, and PCE. PCE is polynomial chaos expansion. This name is very weird, but it's precisely the same strategy that Euclid Emulator 2 used. We have here that all of them are, all our emulators were in below 0.1% agreement. This is very good. We used 400 COLA simulations for training, 100 for testing, so these plots here are very good because they show us that no matter what strategy that you want, you can always use and just get over it if you just want to speed up your analysis. We also use 3 different scale cuts. The scale cuts here are given in K. Okay, so this is H over megaparsec. I forgot to put here. We have 5 different tomographic bins. We use three cutoffs, one that has less nonlinearities, an intermediate one, and a very nonlinear one, okay? So these are our first results. I just want you guys to focus in this first one here, okay, this plot here. So this is the COLA from our emulators with respect to Euclid Emulator 2. The errors here are in %, and we can see that we do very bad when we go to small scales and at higher redshift, because basically this nrefs here means that we just use one reference for the Euclid 2 emulator as an anchor to stabilize our emulators. So basically, what we have is that our first idea of emulating the boost was not as ideal as we wanted, because the error gets to almost 8% at small scales, okay? But if you use the Euclid Emulator 2 reference cosmology, so the data vector is generated using the reference cosmology that we use for our training, of course, we're going to get the same results as Euclid Emulator 2. So this is more or less as a consistency check at the level of the posteriors to show that, okay, we're not that bad, COLA is bad, but if we did something wrong, then not even here in this scenario, we would recover the predictions from Euclid Emulator 2 using the most stringent scale cut. But if we vary the fiducial data vector to something very far away from this reference point here, we get a lot of shifts in the posteriors as we see here. So we're doing very badly. Our COLA emulators are doing very badly. So we go back and we change the strategy from one reference cosmology of Euclid Emulator 2 to multiple cosmologies, okay? Multiple boosts from the Euclid Emulator 2. And this was something that we thought that was going to stabilize our emulation strategy. Because we don't want to create a new emulator using COLA simulations, because it's not going to be as good. Particle mesh code is not as good as we want it to be. There's different ways that we're going to explore in the future of emulation, but for this project, we can see that increasing the number of references to multiple from 100 references, 500 references, and infinite references. So in this case, we need also an emulator for the lambda CDM model. We can see that we go from something that is very bad at small scales to something that is more well-behaved, and it goes to 2% in small scales, k equals 3, in the redshifts that we're interested in performing in our analysis. So this strategy was very good. Vivian thought about the last one, which was very good.
Go back to the sorry, no, right here. So the way you include these multiple references is the right equation. And how do you find the weights?
So yeah, the weights, also the same question, I should have put here the equation. It's just the Euclidean distance between the cosmology that we want to emulate to the nearest reference one. So it's very not fancy, so we can even think about doing this emulation better by better understanding how the degradation occurs in Euclid Emulator 2 and weighing it in a more feasible way. Because Euclid Emulator 2 has 1 to 2% accuracy in an ellipsoidal area of the hyperspace parameter. So if we are in the border of the hyperspace parameter region, Euclid Emulator 2 paper, they already say that they expect the errors to go to 5%, 6%. So in a way, we need to better, in a way, we were as agnostic as possible. We didn't select anything that we wanted. We let everything be. And the weighing scheme is also something that we can think in the future if we want to use any emulator, because any emulator will have a degradation point where we can better weigh this boost here.
So are you confident that you can use this emulator in regions of parameter space that are not in Euclidean, in the Euclid emulator?
So we cannot use it because it was not trained outside of the Euclid Emulator 2. And Euclid Emulator 2 has the broadest parameter space region. So if we compare it with Baco, which was used in some of the analysis of DES, I think, the Euclid Emulator 2 is actually broader, so we can have a bigger prior in our cosmological parameters. And that's why they're creating a new one. They don't want a better in small scales, they just want something that is going to be broader in the parameter space.
So how much faster is your emulator compared to Euclid emulator?
So in terms of performance of running, of just getting a prescription from the boost, I think it's a little bit more, a little bit faster. I think it's like Microsoft. Well, I don't remember. I think that to train this took us like 10 to the 5 CPU hours. Euclid Emulator 2 took 10 to the 7.
No, to call.
To call, I think it's very fast.
Both are fast, right?
Huh? Yeah, so it's faster than Euclid Emulator 2 because Bernardo did something that I don't remember what, that made it faster. This is something that I don't remember. I can ask Vivian if she remembers or scan it. But it was basically a 1 order.
Just parallelization, but it's like both are fine.
Yeah.
The nice thing about this infinite graphs that, of course, if you are very far from lambda CDM in the parameters that are not lambda CDM, this is gonna fail. But the data will kill those parameters anyway. So there's an assumption here is that the data will always require you to be close enough to the lambda CDM subspace that this could work.
Okay. No, but okay. My question is, you're not. Okay, it's a matter of what you're trying to sell here. You're not trying to sell this as a substitute for the Euclid emulator, right? This is a test.
So what we're going to sell here is a viable alternative to extend Euclid Emulator 2, which is very high resolution, very trustworthy. Choose a beyond lambda CDM theory that you have that you want to test. So in this case, we just compare with EE2 because we had WCDM, they have WCDM. So basically, now you can use this prescription of training a Colo simulation, training Colo-based emulators for a theory that is like a reconstruction of H of Z, for instance, that only modifies the background expansion. And you can trust our results to follow this methodology and so on. Okay. So you cannot use this for like a growth of structure that is scale dependent. This is something that we can do later. But as of this is something that you can just rely on modifying the time-dependent things in the background, maybe in the first-order growth equation, and things like that. So this is just this is not to replace E2. This is how to extend E2 or your favorite emulator that in lambda CDM. Okay. So it's a very good question that needs to be addressed. So just to finish now, we wanted this to be below 0.3 sigma deviation, so did not bias the results. So this is the figure of bias comparison for multiple data sets, multiple data vectors that are very weird and very far away from the reference. Okay, our star here is the one that we designed that it would be the best one. So for instance, we can see that it's lying on top, and we can recover the fiducial data vector using this prescription that we are trying to sell here. We can, from here, we can see that we can even use cutoff 3, but this is something that Vivian wanted us to understand a little bit more. It's not only the figure of bias that needs to be small or below 0.3 sigma, but also we wanted the goodness of fit. So for instance, the difference between the chi-square of the E2 chains and our chains from using this Colo prescription to be below 2. And I think that this was a DES year 6 requirement that that Vivian mentioned.
0.2.
Oh yeah, it's 0.2. Yeah. So for instance, this is something that we didn't actually got with the most stringent scale cut in the end. So after using all of these things here of Colo, we just we have a very good. We sold, I think, the intermediate scale cut to be using for your analysis. So just to conclude, what do you want to take from this? Is that Colo and other approaches to model on linear scales, we have very broad models implemented, like in the React code. You have as much as things as we already have in Colo. We need a thorough analysis. So of all of this code, we don't know how much. Like so, for instance, Colo so far was never put to test in this scenario, and React also doesn't have the same level of analysis that we have done here. And this is something that we want to do in the future. The Colo things that we have sold here, they are passing very stringent tests, and the scale cut C2 was, I think it's easy to say that it's safe enough for you to use in your analysis. And the beyond lambda CDM, this is my take. beyond lambda CDM modeling community, we need to understand a little bit better how these things are done in the surveys just to actually get the precision that they want and need. So basically, we just need to get closer to them and listen to them, and so we can all move forward. And I just talked about cosmic shear in this talk, but I want to do galaxy clustering in the near future. Weak lensing mix everything, so baryons, they're going to be very prominent contributions until k equals 10. But we don't know yet how to do this baryon thing, how to model baryons at the level of the matter-power spectrum. There's different post-processing techniques. Also, we don't know how cosmology and baryonic physics are dependent. So after k equals 3, it seems to be they're very much dependent and not independent of each other. They're not orthogonal contributions. So we need to understand this better as well. And for galaxy clustering, it's just because photometric probes, we not only have the convergence field, we also have the galaxy positions. So basically, the 3x2 analysis that I want to do, or basically design Colo to do, also needs some prescription to connect dark matter particles to galaxies in the end. So yeah, this is I think this is it. And let me see if it's yeah, okay. Yeah.
Thank you, Guilherme. So have time for questions? Yes.
Restate my question from the beginning. So what are the data one has to compare to at high K scale? So are they precise enough that you can disentangle these different predictions?
Yeah, so that's the thing. So for stage 3, no. But stage 4, I think, so there's going to be a Euclid paper of different prescriptions of FFR gravity. And there they say that we can see that there's going to be different prescriptions to compute the nonlinear matter-power spectrum. They're going to be giving different results in the end. So we will have the precision, at least for 3x2 in Euclid, they will have the precision.
But the data, they come from the big surveys you mentioned, the ACL, SST, Euclid.
Yeah.
Thanks.
I think the data is even more precise at this case. The data, no, the data, not the theory. But the data is because
the modeling
cosmic variance is smaller. So this is why. Yeah.
Yeah, we need to do better in the modeling, especially in beyond lambda CDM.
Yeah, the problem is not the data, it's the model.
Yeah, that's why I think that like theorists, we need to, well, at least myself, I'm a theorist, but modeling things, not coming up with theories. So we need to do better.
Yes, Walter?
So I have 2 questions. The first one is, when you show the forecast between the comparison of the emulators, and you show a triangle plot with sigma 8, and that one, for example.
Here, this?
The triangle plot, yes.
Yeah.
No, that
This?
one, yes.
Yeah.
So in order to do those measurements, I assume that you use some kind of covariance. So how are you modeling the covariance for the nonlinear scales?
This, we're using everything that is available in the COCOA pipeline, which comes from Cosmolike. Maybe John is better to... Vivian's here, yeah.
We use Elizabeth's cross-code, Cosmocove, actually, to calculate the covariance matrix. So that's like state-of-the-art Halo-based model covariance matrix.
Right.
That includes both the Gaussian component and non-Gaussian, like, the connected tri-spectrum or super-sample covariance. They are all included here.
Right. So yeah, it also models the nonlinear scales, or what is it?
The covariance is fixed at the lambda CDM. So
right. Okay.
So yeah, so we make a same covariance all across because changes in covariance are like not very significant.
Yes.
So yeah, we assume a constant covariance. We change the fiducial data vector. We do not change the covariance matrix.
Okay, I get it.
Yeah, this is good to know also for me.
Yeah, okay, great, thank you. So, and the other question I think is a little bit more general. So, you are using all these emulator techniques to model nonlinear scales in the power spectrum, but can you use some kind of emulator to model higher order statistics nonlinearities? Like, for example, the nonlinearities that you will encounter in bispectrums or tri-spectrums? Or
so these higher order statistics, we need to think a little bit more careful. Like just now, they're going to be like implemented more heavily in these surveys. So approximate
it's a
methods, they
general
were
question,
not...
so it's
no,
for
no,
the-
yeah.
For the future.
No, it's good. It's just because approximate methods were never truly designed or even validated to higher order statistics. High resolution n-body simulations, they are very expensive, and in the sense of for spectroscopy surveys, I think it's more well established because you can use just perturbation theory, and it's not going to be very nonlinear. So in the sense that using the matter spectrum very nonlinear wise, I don't have a very rough statement. I can just say that all the approximate methods are bad.
Okay.
Yeah.
Yeah, okay.
More questions? So I have two. One is the following. So if you go back a little, or forward, no, yeah, before the. So okay. The question is this. So the observables you're dealing here is 3 times 2, basically, no. So my question is about clusters. Can you use COLA to get cluster concentration and cluster profiles in modified gravity?
So we haven't validated that. So the thing is that when we do halo, so for instance for COLA or anything that is particle mesh, we need something that is very thin grid. So the simulations are in the end very expensive to run. So it's 5 times the number of particles. So it's something that is very thin. So we have validated some halo statistics. We have done HOD things.
Yes.
We haven't done per se clusters because in the end, the community was not that interested in terms of beyond-LCDM to do clusters so far. I know that inside of Euclid nowadays we have very high resolution ones from Arepo, and but only for FFR gravity, for instance.
Yes. You have that for FFR.
Yeah.
So number counts, cluster counts for FFR.
Yeah.
With COLA.
No, with COLA no. With Arepo, with something that is very high resolution.
Yeah, the question is, with COLA, is it possible or not?
So we need to validate it first. So it's just going to be a matter of having a benchmark.
In principle, it's possible.
In principle, it's possible.
Okay.
I expect it to maybe not being that good, but yeah, it's possible.
Okay.
Yeah.
Okay.
It's
FFR is dead. Why are we talking about FFR? FFR has been dead for almost a decade.
yeah, but it's easy to.
And this was proposed by Wayne Hu,
exactly.
her advisor.
But we cannot do much. People it's Baoju actually that did the simulations vision.
Yes.
So
yeah, I remember that. Yes. Now the second question. Sorry, go ahead, Vivian.
No. Go.
So the second question will make Vivian go up the wall, but how do you compare this with Cosmo Power?
So yeah, Cosmo Power is just an architecture, isn't it?
We are not trying. You're not trying to sell the emulator here. So we're not trying to sell the emulator here.
So what are you trying
the
to
idea
sell,
here is
what are trying to sell?
Wait.
Cola.
No, wait.
Cola or
The idea is that
Cola.
there is no way, unless, if you want to do serious cosmology, recleansing cosmology in this decade, you have to consider nonlinear scales.
I agree.
So this idea that, and we discussed, that you can just create a dark energy and just do background or linear perturbation. That is that. Well, it's not that in some federal university, but it's another conversation. But it's dead.
I agree.
So So how do you go? How intermediate groups like UNESP, who has a reasonable supercomputer, but it does not, has access to exabyte scales, can do, can do probes in this new era. How can you do you come up with some new, growth factor parameterization or modified gravity and go through the nonlinear scales and do an LSST, do an end-to-end. To do that, you need a way that is reasonable, approximate but reasonable, to get scales at least up to 1 or 2 inverse megaparsec.
And that's COLA.
COLA mixed with Euclid emulator is providing that. And the idea is that before we start this project, people had one way of using COLA in recleansing. We showed that way is flawed, which is based on a single fiducial, and we create a new way to. No energy, yeah. It's like, yeah. Well, the model of my thesis, inflation model, is also dead, so that's okay. You can survive.
The model of my
so we
thesis
create a
is
new
also
way.
dead. The model of my thesis is heavy Higgs. It's also dead. So
Yeah.
we are
Okay.
the same club here.
So what we created is a way to combine high resolution lambda CDM antibody simulations. Example, Euclid doesn't have to be Euclid. With Cola to extend that to additional models in a way that can be used in LSST-Y1. It's precise enough to LSST-Y1.
Okay.
That has never been done before, and that creates a bunch of interesting ideas. For example, what we want to do next, especially with João and everyone at CBPF, is like Booth just invented a new growth factor parameterization. You know that's like a two parameter, they have a 2.5 signal detection. Well, how the nonlinear structure formation works on this model. We are going to do this. We can do that. And we do not need to apply to Santos Dumont for gazillion CPU hours. We can just do that at NASP level, at Stony Brook level. And that's something that it's really important. Like DS use linear scales for a bunch of models that now we can model at nonlinear with Cola.
Okay.
That opens a lot of possibilities.
Okay.
And the emulator is nice because it allows you to do MCMC. We try a bunch of them. We even invented our own. It's called NPCE, that mixes neural network with PCE. But that's not the main thing. The main thing is now we just expand by more than an order of magnitude the range of K modes that are accessible to us in extended models in a way that has been validated and has validated to the stringence of DES, which has never done before.
Okay, thanks.
Yeah,
okay, very good.
I can also say that the other, so for instance, the other approaches, React is not doing as best as us. We're basically a little bit
React,
more
yes.
advanced than them. And React is very heavily like being singled out in Euclid for extensions. So I think that, we need more than one to trust anything. But so far, I think that Cole is doing better. Like even in the paper that we just finished with Ben from React.
Very good, very good.
Yeah.
So
There's another aspect that I like. Is that this is cosmic here, but Nick, great Nick. I'm the only one that's who was the referee of this paper, by the way, has, and that's been shown in the literature, the best intrinsic alignment and the best nonlinear bias model. The problem is that it's a hybrid effective field theory. So theory that needs to be calibrated against simulation.
That's right.
So how do you calibrate that on extended models? So we hope, that's my hope for the next 2 years, to show that these hybrid COLA approaches can actually calibrate effective field theories. And that's going to be a game changer.
So yeah, it was not Nick that did this. It was Shirag Modi. So just to clear out, the Heft thing is not from Nick. So just, but yeah. So
okay.
Yeah.
But we like Nick.
Yeah.
Anyways.
Yeah.
Okay, so now I guess it's time for feijoada. So sorry, Vivian, you're not going to join us for feijoada today.
Vivian needs to come here.
You need to come here. Yes, absolutely. Okay.
You get a feijoada. How are you going to work after feijoada? Like feijoada is from Shabbat, like that. You just eat feijoada and just leave.
No, after feijoada, we have the colloquium, which is the... Oh, this is being recorded, so I should not say anything.
Oh, yeah. 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 Here.